it's okay. We can go. I guess most of the people will join up later. Okay, so let's go in the atlases. So Georgia, I corrected. Thank you for correcting me. Atlases is what with one S. So let's see atlases. So this is really a very intuition notion that you learn in geography, or if you are a traveler, right? You are driving around the world. You buy your atlas. So this is really an abstraction of that. The atlas that you buy in the bookshop, or you learn in cartography or whatnot. Is made of charts, right? So in abstract, when you have an n-dimensional manifold X, an indexed collection of charts that we will write like this: A, made of these this collection, this index collection by an indexing set I, is called an atlas if the union of all the chart domains, the UIs, will recover X. Okay. And another thing, obviously, there is no restriction on what the I can be. This can be infinite. This can be finite. So the indexing is arbitrary. It can be anything. Okay.
Does it need to be countable?
Yes, that's a very, very good question. Yes, countably infinite. That's what you want. If it's uncountably, you will have a lot of extra work to do in order to get around even some of the most basic stuff. So yeah, it's generally you want to assume if it's you want to index it with an infinite set, you want it to be countable in a way. So obviously from the definition of an n-dimensional manifold, there is always an atlas. Whether it's useful or not, that's another thing. This is also related to your thing about countability and this type of stuff. So there's always an atlas, because every point of the manifold, there is always a chart domain around that point, right? So there is always an atlas. It might not be useful, but the definition of the manifold already automatically guarantees there is at least the existence of an atlas. Okay. Now we want very specific type of atlases, so not every atlas. This is the whole point of this session. And one thing also I want to, this is obvious for you, is that obviously the chart domains are open covers, right? So you remember the stuff in point set topology, open cover. And I guess this is like, I don't know why I'm even asking this, whether the other way around is true. Obviously this is not whether an open cover is necessarily an atlas. I think, yeah, you guessed the answer. Okay. So here's a simple example. This is the simplest example because obviously Rn, for example, is one of the simplest examples of an n-dimensional manifold. So the claim is that this is a chart. I mean, this is an atlas. This single chart can actually also provides you with an atlas. It satisfies this, right? If you take a union of Rn is Rn, and obviously this is this guy here. This is this provides you with the thing with this is a homeomorphism. So this is a chart. So this is this is an atlas. This is called the standard atlas. It might not be very very pretty, but it is an atlas. Oh, so we have more people here. Okay, so I assume this is all easy. This is where it starts to become more so. An atlas is just a collection of charts that cover the entire space, essentially. Just like your intuition of what an atlas is, when you buy an atlas from a from a geography from a bookstore or something. Okay, now here's some comments that I would like to go. This is also for you to have some food for thought to go and think about this. First of all, as I said, we are not interested in any type of atlases. We are interested in smooth atlases. These will be atlas. In fact, not just smooth atlases. You know what a smooth atlas is? I think we defined that last week, right? An atlas that we defined last week. George, we defined a smooth atlas last week, right?
I think we defined a smooth chart.
We didn't define the okay. Yeah, we will define it today. Yeah, you see my thing. We defined the charts, smooth charts, but as you will guess, as we'll get into it, a smooth atlas will just be a collection of charts that are smooth compatible with each other. You will see that definition actually. I'm already ahead of my time. This is what happens when you have 2 weeks breaks. You forget what you have covered or not. So anyway, so I'm already giving you some hint here. And also something very interesting you might think is that based on the previous definition, for example, you can conclude, it's very easy to conclude, especially the advanced guys, that a smooth, let's say a CK manifold or differentiable manifold is just a manifold equipped with a CK atlas. Similarly, you will say that a smooth manifold is just a manifold equipped with a smooth atlas. Okay, we'll get to the thing, but this is not the thing. I want you to come back to this as we go along the definitions to see that this definition is a little bit ill-defined. So I want you to come back to this after we go through the next few slides. I'm now starting to think that I've messed up with my slides, because if we didn't define a smooth atlas, I think I forgot one slide. I'll just stop sharing because it might be, I'm pretty sure I've the thing. Can I just stop sharing? I'll go back to the slide. I must have messed up with the.
It's easy to.
Didn't we define smooth atlas last week?
we didn't do anything about atlases. I'm fairly sure we defined a smooth chart.
Yeah. Let me check my thing. I'm going back to my LaTeX. Sorry for that. Let's see. That's because I was also rushing in the thing. Did I forget? Just give me a second. I'll go back to my thing. My LaTeX, original LaTeX. This is what happens when you do things like in a rush. I promise we'll finish on the hour, so apologies for this.
I'm sure the final slide deck will be good.
Yeah.
It's actually harder than with a blackboard. With a blackboard, one smooth move you erase and redo.
Yeah. Just going back. So I have smooth on the current slides. I'm just looking at them. I have compatibility of smooth atlases, but obviously we need to define first what a smooth atlas is. Let me check.
I think you might need somewhere just to define the gluing that there's, even in the non-smooth case, this relation between neighboring charts that overlap.
Yeah. So actually, I found the thing that I didn't integrate in here. So it should be. Let's see. There's one slide that I forgot, which is the CK, the one that defined CK and smooth atlases. So you have to give me 3 minutes, 2 minutes or so. I'll recompile this, And then I have to do these slides again, the editing, integrate this. In the meantime, those of you, feel free to be chatting on the, to do the conversation on the chat while I do this. It's a whole new experience, huh? Where is it? Dun, dun, dun. Ah, okay, so there you go. So this is it. So give me 2 minutes, I'm done. I will obviously edit this break here to jump to the point where we have the smooth atlas stuff, so people rewatching this are not having to wait like you guys are doing at the moment. I hope I didn't forget any other slide. So let's see. I think with this we should be good to go. Is there anything on the chat? By the way, I'm not looking at the chat at the moment, so there's no one.
No, all quiet on the chat right now.
Okay. So I'm pleased to announce that we are back in business. So let's see. I hope I didn't mess up with the ordering of the chats. Okay, yeah. So I will start sharing again. I think I've integrated the. Now I cannot find the share button. It's here. Okay, so we are back in business. So this is where we were, right? About Atlas. I think this is all understood. Nobody has any doubts about this. An atlas is just a collection of charts, that cover the entire space, right? And as I was saying before I was jumping gun, is we need special type of atlases. So not every atlas, even though, by definition of a topological manifold, there is always an atlas. We want specific type of atlases. So this brings us to these guys here, CK and the smooth atlases, okay? So given an n-dimensional topological manifold X and a collection of charts, an atlas, we can make these two definitions. We say the atlas is CK atlas if given any two charts, U1 phi 1, U2 phi 2 in the atlas, the two charts are CK compatible for some K greater or equals to 1. Remember, I think we defined CK compatibility, I'm pretty sure last week, right? I mean, in the last session.
Yeah, and that is maybe something in a review session. That's something that you should recall from multivariate calculus or even single variate calculus.
Yeah. So all it means in a nutshell, these maps that we defined in the last, so the composition, these composition maps are CK maps for some K. So that, remember, I think Barry made a very good observation that these transition maps are maps from parts of Rn to another part of Rn. So these are from Rn to Rn, so we can talk about differentiability and these things. Okay.
That's absolutely the magic.
Yeah, to understanding. Yeah. So thank you for putting that, Gary. Barry. So it's important to always know that these transition maps, these are actually parts of from part of Rn to another part of Rn to an open part of Rn to another open, right? Because these are like homeomorphisms also, right? So this is called CK. If it's CK for some K greater or equal the thing, we say the atlas is greater or equals to 1. We say an atlas is CK atlas. Likewise, similarly, if these two guys, if giving any two charts, if the chart transition maps are smooth compatible, then I mean, if these two charts are smooth compatible, meaning that again, these maps are both smooth maps. You know what a smooth maps? The definition of this, I think we also did that. Smooth maps from Rn to Rn. That's what we did, because remember, these guys are from Rn to Rn. We'll have a definition of smoothness in the thing directly from manifolds in the next session. But the smoothness that we are talking about here, this is from Rn, part of Rn to Rn. So it's not an abstract in a thing that which we will do in the next session. Now, something that you also probably noticed, I think I asked the question in one of the sessions, in the last session or something, the relationship between these, you probably noticed that they are inverses of each other. So which implies that they are actually diffeomorphisms on Rn, okay? So it's very important to notice this, that these guys are diffeomorphisms. We will define the notion of diffeomorphism itself in the abstract from manifold to manifold, but this diffeomorphism here, this is from diffeomorphism on Rn, which I think we covered. I gave it, there's a section called diffeomorphism part 1. We'll have a diffeomorphism part 2 where we'll have an abstract definition of it, but direct between maps on a manifold. Okay, so now this makes sense now, the comment. So we know what a smooth atlas is. So a smooth atlas is an atlas whose, when giving any two charts, the two charts are smooth compatible, okay? So this already hints you that we are interested in, smooth atlases. So this then makes sense. This thing that this comment here is that you might jump to the conclusion saying that X is a CK manifold if it has a CK atlas. Similarly, X is a smooth manifold if it has a smooth atlas. But this is not enough. We need extra conditions. And the challenge for you is to think why this is ill-defined, this is incomplete. This wouldn't be just leaving it, defining the notion of a smooth manifold and or more general of a CK manifold, just without any extra condition, just with the CK atlases and smooth atlases is not sufficient. I let you to think about it as part of solidifying your knowledge as we go through this stuff. So this is where I will make the choice now that from now on, we just want smooth atlases, okay? So atlases that satisfy this. But a lot of the definitions can be done with the CK also. So therefore, it's just a matter of, as a challenge, actually, you can try to translate some of the stuff to generalize it to CK instead of just sticking to the restriction of smooth cases. Yeah. So another comment I want to make is this one, is that it's very important to know which, once you fix an atlas, you like an atlas, it's very important to know which other charts on the manifold you are allowed to use with, right? So ideally you want, I know I haven't defined yet the notion of a chart atlas compatibility with an atlas, which is what we'll do in the next slide. So ideally you want, you only want to use charts that don't destroy the smoothness of the atlas. Once you choose the atlas, you want any other charts that you want to use, they should not destroy the smoothness of A. So in other words, this is what we call the charts must be compatible with A. And the definition of that, the formal, before that, actually I've swapped, before that we have this challenge. This is the things, the challenge is, I've given you these charts. The question is, whether this is an atlas in the thing in the circle, and whether this also an atlas on the thing, if this is an atlas on the thing on the sphere, and whether they are CK or smooth atlases. Well, you just look at the maps and go to the definition, and then you should be able to answer this. I hope I haven't made any typo. And now finally, the definition of compatibility that I was just mentioning. So when you have an n-dimensional topological manifold together with a smooth atlas, another chart on the manifold, let's call it U tilde and phi tilde on X, is said to be compatible with the atlas A if the transition maps between U tilde, phi tilde, and any other chart on the atlas are diffeomorphisms. Okay, but diffeomorphisms, remember, on Rn, right? Because these guys, the transition maps are again maps on Rn. Okay, so if that happens, we say that this chart is compatible. So another way to say this is if this is too abstract, too confusing, another way to state this is this: is that if you take the U tilde, phi tilde is compatible with the A, if when you do the union between the atlas A and you add this chart, the result is still a smooth atlas. Okay, so this is another way of seeing this, if this is confusing to you. So essentially it means if you add this to the existing atlas, you don't destroy the smoothness. The atlas is still smooth. You will still generate another smooth atlas. Okay, so if that happens, we say, well, this is compatible with this. And likewise, now you can generalize this. That's why I could have started like this, but I thought it's easier to do it this way so you can see where we are heading. Likewise, you can generalize this to compatibility between two atlases. Okay, so two atlases, A1 and A2, smooth atlases, they are compatible if every chart in the second atlas in A2 is compatible with A1 in the sense of this definition. Again, another way to see it is to say that A2 is compatible with A1 if and only if the union of the two charts also results in a smooth atlas. Okay, so you don't destroy. If you do the union of the two, remember these are sets, right? They are a collection of charts. So you are allowed to take the union, right? You take the union. If the result still smooth atlas, then you say the two atlases are compatible. Okay. And now here's a proposition that I will leave for you as a home challenge. It says that given two atlases, A1 and A2, that are compatible, okay, smooth atlases, okay. If a chart U tilde, phi tilde is compatible with the first one, A1, then it is also compatible with the second atlas. So this is essentially implying that the compatibility, the notion of compatibility defines an equivalence relation on smooth atlases. In fact, this is one of the things, some books, that's one of the reasons I'm commenting here, some books use this equivalence class of compatibility to define the notion of a smooth structure. But we won't do that because I think it's a little bit confusing to do it that way. So we will take the other approach, which is to use the notion of a maximal atlas and these things in order to define the smooth structure. But some books, especially classical ones. So I have a question. Is that, so I have, how many questions I have here? I cannot see. I know there's Barry's question,
okay.
I cannot see it.
There's two questions, one from Barry, one from Amir. Do you need me to read them or can you see them?
I can, maybe you can read them today. They are a bit small because I'm on presentation mode. Somehow it's a bit.
I have a little screen magnifier I can bring up. Barry had asked, once you've chosen an atlas, why would you want to use a chart that's not in the atlas? Doesn't an atlas have all you need to do calculus on the manifold?
That's very interesting, but very good question. Yes. So you say, for example, you fix is the same answer as if you ask me if I have a chart. It means that I've given certain coordinates to the manifold. You know, why don't I stick the thing? So the answer is that you might have an atlas, but then maybe that atlas doesn't have, you know, there might be some other, you want to make you want to, for some, you know, maybe for some problem or something, you know, you might want to go from use other charts from another atlas in a way. This is what the definition is leading you to. So it gives you the freedom to switch from chart to from one set of charts in one atlas to another set of charts in another atlas. Okay, because there might be some problem that you chosen one particular atlas, but then maybe you have a problem that's better off solved in other charts that don't necessarily belong to the atlas that you have chosen initially. All we need to do is George, you were going to say something?
And Amir's question was actually rather similar. Why would you want to add a new chart if the atlas already covers the space?
Yeah, you will see, I guess, as we go along, you will actually be able to answer this. This is all like a technical toolkit to get us to the notion of a compatibility of the thing of a maxer to give a smooth structure.
Yeah, my question would have been the opposite, and maybe we'll be leading up to it, is how many charts can you remove and still have an atlas?
Yeah, that's very, very good question. Let's we'll come back to that. And Amir, we'll come back to your thing in a minute.